So today we have a FE environmental example that makes use of the Phelps formula in the new FE handbook. So for this question, if we read it slowly, we're told we have a factory discharges its waste into a river flowing at a velocity of 5 km per day. After mixing with the waste, the river has an ultimate BOD concentration of 15 mg per liter. The initial dissolved oxygen concentration is 8.2 mg per liter, and the saturated oxygen concentration is 8.9 mg per liter. The reaeration rate is 2.2 per day, and the deoxygenation rate is 0.1 per day. The concentration in milligram per liter of the dissolved oxygen till 10 km downstream is most nearly what? So we want to find the concentration 10 km downstream in the river, right? So real quick, if I draw a picture, what we're actually given here. So to draw just the basic image, let's say you have a factory, it discharges, so we have our factory. So let's say this is our factory, and we have, let's say it discharges through a pipe, right? And it discharges some waste, and I'll use red for the waste. So this is our waste here, and this waste is discharged into a river. So let's draw the river going this way, right? This is our river, and let's assume it's flowing in this direction at some velocity, right? Vector velocity v. So we introduce this waste, and we know when we introduce the waste, we're influencing the oxygen, the dissolved oxygen concentrations. And that's the whole point of the Phelps formula, to model that dissolved oxygen curve, or they call it the Sac Curve. And we're going to essentially do what? Find the dissolved oxygen concentration 10 km downstream. So downstream is going to be somewhere down here, right? So we start at 0 here. This is 0 km, and we're gonna find the dissolved oxygen concentration somewhere down here. Let's assume 10 is here, right? 10 km. We will find the DO value, right? Downstream, after the waste has been mixed. Note here, the waste is gonna go into the river, right? So that's what we're doing here, and that's a basic picture. So let's begin writing the variables that were actually given. So we have the KD and KR value. So in the FE handbook, just note that KD is the deoxygenation rate and KR is the reaeration rate. So let's write that as KD, use black, KD is going to be the deoxygenation rate is 0.1 per day, right? 0.1 per day. And let's write KR, the reaeration rate, is going to be 2.2 per day. And note the formula in the handbook, make sure to know it's on page 320, stream modeling Phelps equation. And all the variables are defined. So we know we have those. So we took care of this, we took care of this variable, and we're told the ultimate BOD concentration right after we mix. Note that this BOD is as soon as we mixed here. Let's call this, for example, the mixing zone. So this is where this occurs, mixing zone. As soon as we discharge the waste from the factory into the river in the mixing zone, we will have a BOD concentration, and that should be given to you in the problem statement. That's 15 mg per liter. And in the handbook, that's denoted as the initial ultimate BOD in mixing zone. So that's LA, right? The LA variable. So for that, we will say it's 15 mg per liter. So we have that. This is out, right? And the velocity, so the flow velocity is 5 km per day. So let's just denote that as V. It's a velocity. It's 5 km per day. For that, and that's taken care of. So the only other two variables that we haven't described is this 8.2 and the 8.9. The initial dissolved oxygen concentration is just that. It's the dissolved oxygen concentration initially. So in here, right, in this region. So I'm gonna denote that specifically by calling it DO initial. Note, this is not the deficit, right? It's different than the deficit. We will describe that in just a second in the figure, but the initial there is 8.2 milligram per liter, and the saturated oxygen concentration, DO sat, this DO sat is actually described in the handbook, right? Saturated dissolved oxygen concentration is always DO sat is 8.9. That's given milligram per liter. So the end goal again is to find the concentration of dissolved oxygen here, 10 kilometer downstream. So let's write that as what we want to find. So DO concentration, and I'll just do a subscript of 10 kilometer. That's what we want to find here. So let's do the solution and dive into this. And before we jump into equations, let's quickly look at the Sac curve. So what I have here for us is, we know we introduced the pollution, right? The waste. And we introduce it as some x distance, which is the starting distance, right? In the river. X equals 0, right? We start at 0. And that corresponds to a time t equals 0. So that's where we introduce the pollution. And this is also related to this graph, right? We know that we start at 0 here for the distance or time, right? And over time, we know the addition of this pollution, as shown here by the brown, the addition causes a decrease in dissolved oxygen. This dA is going to be our initial dissolved oxygen deficit in the mixing zone. At times you do not have a deficit, but we know in the handbook it's described. So make sure if you have a deficit, you must consider it when you use the Streeter-Phelps equation. And that deficit is measured from the DO sat to the bottom, where we know we have that initial dissolved oxygen concentration that's actually given in the question. And that's going to be this, right? DO initial. So actually in this figure I did not label DO initial, but we know DO initial would be this whole distance, right? We measure it from the bottom, so this is going to be our DO initial. That's our DO initial. So we know DO sat minus DO initial would give us dA, and we'll come back to that as we solve the question. But at the end, we know that we start here, we have a Sac curve, right? We have a Sac curve, and this portion that's highlighted at the moment is where we have decomposition. So the BOD, or the carbon, is getting eaten up by bacteria or other aquatic life, and they use oxygen. They use a lot of oxygen to essentially eliminate the BOD. So a lot of oxygen is being used. That's why we have that sag, right? Then we begin to have re-aeration. So we begin to have photosynthesis, and most importantly, we begin to get oxygen from the atmosphere, right? So we have re-aeration in this case. We have the addition of oxygen. Then we hit a saturated level. We hit the DO sat. And just note that this phase, again, is where we have re-aeration and oxygen being added, and the way it's added is from the atmosphere, and that depends on Henry's law. So it's from the atmosphere where we get that oxygen. And one important thing is DO min is the minimum. It occurs at the very bottom peak, right? DO min, the minimum dissolved oxygen, and that corresponds to a critical time or a critical distance. That critical time has an equation in the handbook, which is not applicable in this example, but just note that it occurs at the bottom. And at this DO min and XCTC, we know the decomposition is going to equal to the re-aeration, or the how much oxygen is added. So decomposition equals to reaeration at this point. So that's all of that, but the end goal here for this question, if we use this figure, is to find 10 kilometer. So we know at somewhere downstream 10 kilometer, I'll call it here, let's say it's here, x equals 10 kilometer. We have a t, we will have a t of 10 kilometer. So what's the time at 10 kilometer? So we need to find that time, then we can use that time and plug it into the Streeter-Phelps equation, right? So we will say we're 10 kilometer downstream, and the end goal is to find that DO, this value. So we will find this DO by taking DO set minus the deficit, right? And that equation is in the handbook. To find DO at 10 kilometer, we take the DO set, the saturated, minus D, which is the deficit. So anything here is the deficit, right? And that will give us our answer. So that's what we will do. I hope that made sense through this figure, but let me know if you have questions down there. So let's begin, and we will first find the time. Again, we need the time 10 kilometer downstream. So that's step number 1. Let me write that as 1. So we will find the time, and we know simply the velocity is distance times time, or we can say the time is going to be the distance divided by the velocity. So the time at 10 kilometer downstream is going to be the distance, x, divided by the velocity. So the distance, we said it is 10 kilometer, right? We want to find 10 kilometer downstream. So we do 10 kilometer. Velocity will be what? The velocity is given to be 5 kilometer per day. 5 kilometer per day. And the kilometers cancel, so we get the time when we are 10 kilometer downstream is going to be 10 divided by 5 is just 2 days. So after 2 days, we need to find the DO, dissolved oxygen concentration, using the Streeter-Phelps modeling equation. So now, step number 2 is the tricky step, is we need to actually determine the deficit, the initial dissolved oxygen deficit in the mixing zone. So we'll call that step number 2, and this is finding initial dissolved oxygen deficit in mixing zone. So that is going to be arrived at by employing this equation. We're just going to say dA is DO set minus DO initial. So we know that's actually true, right? Because we will say that DO set is going to be this entire distance, right? That entire distance is DO set, the saturated dissolved oxygen. We will take DO set minus DO initial, and that gives us this, right? The deficit, the initial deficit in the mixing zone, dA. And we know DO initial is actually given in the problem statement. Just know the initial dissolved oxygen concentration is 8.2. If they say on your FE or in the problem, the initial dissolved oxygen deficit, you would just use that value. But here it's specific. It's the initial dissolved oxygen concentration, right? Deficit is different than the concentration. So we need to find the deficit. So dA equals to DO set, which is going to be 8.9 milligram per liter minus DO initial, which is 8.2 milligram per liter, and that equals to 0.7 milligram per liter. So we need that dA when we use the final formula. Now we will find the deficit, the oxygen deficit at 10 kilometer. So we're going to find this value, right? The D value now. And that D value can be found by using the equation in the handbook, right? The Streeter-Phelps deficit equation. So that's 3. We will find the dissolved oxygen deficit after 10 kilometer. So doing that, we know D is going to equal, so the whole equation is this: D equals KD times LA, the BOD in the mixing zone. Then we take KR, the reaeration, minus KD, the deoxygenation rate constant. Then we do the brackets. So it says EXP in the handbook. That just stands for exponent. The exponent E. And we take negative KD, the KD value, times T, times the time, which we already solved. And I'm going to use the time in red, times the time. Then we close that, minus E, and we do negative KR, so the reaeration constant, times T, and we know T again is the time. Close that, then we close this whole bracket, then plus dA, and we do E to the negative KR times T, right? Times the time. Okay, close, and I believe that's it. So we do D, that's going to be the deficit. We do KD 0.1, LA is going to be 15 milligram per liter. Then we do KR is going to be 2.2. No, the units for these, this is per day. So everything at the end should work. Make sure everything is in days and everything is milligram per liter, the concentrations and time, right? That's 0.1 for KD. Then we do this, E to the negative KD. So we know KD again is going to be the same as this, so it's just 0.1. And we multiply by the time. We said the time is 2 days, right? Downstream at 10. So this is 2 here. Close that, close. Then we do minus E to the negative. KR is going to be 2.2. Then times the time again, which is 2. Close, and close bracket. Then we need that dA, right? If you have a deficit, you always include it and add it. So in this case, it's 0.7, that deficit. We found that. 0.7. That's going to be in milligram per liter times E to the negative. KR is going to be 2.2 times T, which is 2. Close that, close. So you can break this down, do the brackets first, then simplify this, then break it down however you find reasonable and good for you. But here I just plugged it all in the calculator, and I believe we should get about D, the deficit, equals to 0.585 milligram per liter. So now we have the deficit, right? We have this value, and how do we get DO? What we do is they take DO set, so we're going to take this whole value, which is our DO set, minus this value, which is the deficit, and we get DO, right? So that's the dissolved oxygen concentration at that time, or at after 2 days at what, 10 kilometer. So let's do that. That's the last step, step 4. And the equation for that is actually in the handbook. So it says DO is DO sat minus D, but I'm gonna rewrite this as DO at 10 kilometer is gonna be the DO sat minus D, the deficit we just solved. So this equals to DO set is gonna be 8.9 milligram per liter minus D, which is 0.585 0.85 milligram per liter. So then if you do the math, we get 8.32 milligram per liter. And that should be our answer. So I believe in this case, it's gonna be B. So that's all for this. Let me know if you have questions. Thank you.